Okay, so live stream running. There are still some questions on Campus Wire that I really feel some of you can answer instead of me doing it. Which is only partly because I'm lazy and don't want to answer it. Mostly it's for you to have this experience of learning by teaching. All right, I think I'm good to go. I know it's lovely weather outside today, so there's many other good places to be, but there we are. And let's talk a bit more about compression. It doesn't compete with the nice weather, but it is some cool topics. I hope so. I hope you agree with me in saying that. Remember last time we talked a bit about Huffman coding, which was, in a sense, the best way to choose code words for individual characters. So it was the best way if you were decided for each alphabet character you assign some code word of variable length, then Huffman codes gave you the best way to choose these code words, or at least the lengths of these code words. And we already saw that we saw this theorem last time. What I just said in words is spelled out there in formulas. If you want to get what's called a prefix-free code for the individual characters, then a Huffman code gives you the best such code, no matter what the weights look like. And in particular, you can apply this where the weight of the character is the number of occurrences of that character in a given text. That's where we left off. So we showed that Huffman is the best possible such code. Huffman codes are the best possible such codes. What else would there be left to say? In this section about entropy, we will have a look at how we can quantify how well Huffman coding will work without running it on the text, but just by analyzing the text up front. And we'll come to statements that are more versatile than just analyzing Huffman codes. We've seen Huffman codes are the best possible prefix-free character codes, but we'll look at other compression methods later on. And so, yeah, Huffman codes are the best of this specific family. It's not necessarily the best overall for all sorts of scenarios, but entropy gives us a way to evaluate how well Huffman codes would work on a given text without trying it out, just as an analytical way. So let's start with the definition. That's just something that falls from the sky without much motivation at this point, but I'll try to motivate it, give the intuition behind that definition right after. The entropy is defined for probabilities. So we have here p numbers. They're between 0 and 1, and they sum to 1, so it's a probability distribution. So what that means is p1, p2, up to pn sums to 1. And also each pi is between 0 and 1. That's, well, as you may have seen in other courses, that's probability distribution where we have n possible different outcomes. And the entropy is defined for the distribution. So it depends on these probability weights. And it's just this sum. So we sum pi times log of pi, logarithm to the base of 2, and a minus in front, or this is the formula I think it's a little more intuitive, so I would like you to keep this one in mind. It's pi times log of 1 over pi. So why might it make sense to make this definition? Well, first of all, I've just thrown this definition at you and haven't told you what we'll use it for. The idea of entropy is to have a measure of information content. Now, what's the information content of a distribution? That's a bit unclear, maybe. What we mean by that is if you draw a random sample from that distribution, a single random variable that's distributed according to this distribution, and then this variable will have one specific value. But because it's a random, expected values. And so the entropy gets at the question of the expected number of yes-no questions you need to answer to nail down the value of this random variable. Okay? So in a sense, if you know this game of 20 questions where you ask 20 yes-no questions and try to nail down a specific thing that your partner thinks about, then this is in a sense what the yes-no questions in entropy also try to do. So let's try to see an example by what I mean by this. Suppose we lay out the probabilities. So this P1 up to Pn, I can draw this unit interval, and I can put in the probabilities here. So suppose the length of this, that's my P1. The length of this is P2, and so on, up to Pn. Because they sum to 1, this has to go up and cover exactly the unit interval. And then the outcome of this random variable is selecting one of these intervals. So in the picture here, there's one of these intervals is red, and that's the one that this variable actually took. Now let's try to figure out yes-no questions that allow us to find out which of these intervals was selected. And so the best thing you can in general do if you start with this interval, at the start you know nothing. You know the red interval is somewhere in the unit interval, but that's all. And so you try to ask a question that with one yes-no question maximizes the amount you learn. So I guess the best and intuitive way of doing this is asking whether the value is left or right of the middle point. Okay? So you ask this question. It's a yes-no question, or well, it's a left-right question. Is it left? Yes, no. Okay. In this case, it's on the right side. And so after the answer to that question, you asked one question and you learned now the interval is somewhere on the right of the middle point. Okay? And you keep going like this. You cut it in half another time with another question and another time and one more time. And then if you know that, you remember this picture from above, if there were these intervals for the PI, if you've nailed it down to this range, maybe that's all we need, and then you know the value. That's a single interval left. So if the probability here is this distance, the probability of falling into this red range is the difference between the endpoints, and that's 1/16. If that is the probability, then this value here, log of 1 over the probability, is 4. Because 1/16 is 16, and log base 2 of 16 is 4. Now, how does this match up? This number of 4 is exactly the number of times we had to cut the unit interval in half before we arrived at that size. That's, after all that the logarithm expresses. And so this quantity that we sum up here is, in a way, the number of yes-no questions you need to make before you get down to this size. It's the number of times you have to cut the unit interval in half before you reach a certain size. And this is what we define as the information content of that outcome, because it took you so many yes-no questions to get there. And then the entropy is just averaging that over all possible outcomes. Each PI occurs with probability PI, or each outcome I occurs with probability PI. And it took you log of 1/pi questions to find that. That's the rough intuition behind entropy. Okay, that's why this term might make some sense. But we'll put it into more concrete context with Huffman codes on the next slide. In general, if we have a random value, then we ask how many questions do we need to nail down that specific value. And here I identified the value with the position of the interval. So I labeled the intervals from left to right, 1, 2, 3, up to n. And then finding out if the random variable is in one of these intervals is the same as finding if its value is a value I. But no matter what the values really are, you can always draw the probabilities as these intervals in the unit interval. So it seems, at least from this intuition, that we would like to encode a value I, if it has probability pi, using log of 1 over pi bits, because that was the number of yes-no questions we used before. Okay, so far I can only appeal to your intuition that maybe this makes sense. But at least it already is clear that this is not quite possible, because log of 1 over pi might be some real number, definitely not necessarily integral. And so it's a little tough to see how we can create code words with length 1.5. This sounds, if you think of specific code words, there's no binary string of length 1.5, but you can sometimes achieve this on average if you don't have a fixed code word, but you have the option to average things out. Then you can sometimes indeed achieve this. It's something that we won't cover, but there's a method called Arithmetic Coding that is Huffman on steroids. I don't know. It allows you to do this, to code things with a fractional number of bits. But yeah, we'll leave it with Huffman. So in Huffman coding, we cannot do this. So it seems like as long as we have a Huffman code, we have to somehow round up. And that's also what we see in this result. So let's parse this step by step. We have some alphabet sigma again. So we have characters 1 up to sigma, or A1 up to A sigma. And they have some weights. Again, think of the weights of as relative frequencies or probabilities. And we have a Huffman code. So that's the code from last time. I showed you how to compute that one. And remember, L of the code, that was this expected code word length. So L of E, oh, don't do this to me again. We sum over all the characters. And what do we sum up? The weight of the character times the length of the code word. That was the definition of this L. And now this theorem says I can look at an entropy. So H, this calligraphic H, is what I'll use to denote entropy as defined here. And now we take the relative weights. Okay, so these are exactly the weights, but we divide by their sum. And if the weights are probabilities, then the sum will be 1, and this is just the entropy of the probabilities then. But in general, it's convenient to allow weights so that we can just put in frequencies. I take the relative weights, I compute their entropy, and it turns out that this is a very tight bound for how well Huffman will do, how well the Huffman code works for these weights. The code is uses at least as many bits on average than H. And it turns out H is a lower bound. You can't possibly beat that. And H plus 1 is an upper bound. And that comes essentially from the fact of this rounding. If the entropy tells you, please use 1.1 bits, you can't really do that. You have to round it up. And if you do that rounding up all the time, you essentially lose this plus 1. We'll see that in the proof. Is the statement clear? So you compute a Huffman code for a given an alphabet with some weights. And this theorem tells you quite precisely how long on average a code word will be. If you take a random character, then the expected length of its code word will be between h and h plus 1. Let's sketch at least how we can prove this. There's two parts. The first statement is the lower bound, that L of E is bigger than H. And we will prove this not for a Huffman code E, but really for any prefix-free code, because the statement is true for any prefix-free code. If we have a prefix-free code E, then we can choose weights. That again is just a definition, but it has an intuition as well behind it. So the QI are defined as 2 to the minus the length of that code word. And that comes from the idea that each bit you spend in the code words is something like a question, left or right. And so whenever you spend a bit, you should cut down the probability in half. And so these QI are exactly defined so that every bit cuts things in half. There's something called Kraft's inequality that shows that if you do this, you get to at most 1. And the intuition is if you draw the trie for this code, remember the code trie looked always like this. We have 0, 1, more edges 0, 1. And maybe then here in the leaves, you have the characters. Okay, remember code tries, Huffman codes, etc. It was important that the characters are only in the leaves. The alphabet symbols are only in the leaves. And what this says is if you assign a weight of 1 to the root, and then assign half of that weight to its children, and half of that weight to their children, and half of their weight to their children. I think it's clear if you go down one step, the weight on one level is always summing to 1. It started with 1, and then you exactly split it in half, so the sum is still 1, and that keeps going. And what you can also show is if you take any cut through this tree that doesn't contain 2 nodes where one is an ancestor of the other, then they also sum to at most 1, because you cover at most 1 level just shifting things up and down. The idea here is you could pretend that these go down 1 more level, and then they go all to 1/8. Okay, then no one can read this. If you go down to the level of the deepest leaf, you will have a power of 2, and that is the number of leaves on that level, and those sum to exactly 1. If you combine 2 of these into the 1/4, their sum is still the same. And so if this tree is full, if you don't leave out any nodes, you will actually sum to exactly 1. And you can leave out some leaves, then you sum to at most 1. All that Kraft's inequality says sum is at most 1. Then there's another inequality, Gibbs inequality, that applies here. So this part is Gibbs inequality here. I don't want to prove it, but it's a standard result in probability theory. So let's just use that as a black box. It says when you have something that sums up to at most 1, then you can replace in the entropy formula the p's here by the q's there. That's Gibbs lemma, Gibbs inequality. So we write down the entropy, use Gibbs inequality to sum over the qi here instead of the pi. And this sum is exactly L, just written in a different way. Because here, if you plug in what qi is defined like, then this 1 over becomes 2 to the length of the code word, and log base 2 just takes the 2 to the away. So what you're left with is the sum of the lengths of the code words times their weights, and that's the definition of this L. Okay. So that's the lower bound. And all we used here is that we have a code that is a prefix-free code, so that we can draw the code trie and use Gibbs inequality. But it also holds for Huffman codes in particular, because they're an example of a prefix-free code. The second part of the statement is this upper bound. If you have a Huffman code, it is never worse than h plus 1. And for that, we do something similar, but we'll just construct such a code with a similar construction. We again define QIs, which are similar to probabilities, but they're defined by taking 2 to the minus and then this ideal quantity, log of 1 over p, but rounded up because we can't really deal with fractional bits. Now, if you have a code of that length, its code length, it's L, the expected code word length is this, sum pi times log of 1 over qi. That simplifies to this, just plugging in, same trick as before. It's the proper choice of the qi so that log becomes something nice. And here, not again, what we use is that if you take ceiling of some number, that's never more than x plus 1. So if you use that here, we have the number is x, and then you split the sum. You sum up pi times log of 1 over pi. That's exactly h by definition. And you're left with the plus 1. And that means what's left is the sum of all the probabilities, and that's 1. That's where the plus 1 comes from. So if we can construct a code where the code words have length log of 1 over pi rounded up, we're good. That proves this statement. If we can show that Huffman codes are never worse than that. And what we'll do is we construct some code which is not necessarily a Huffman code that has these code word lengths, but then we use that Huffman codes are the best possible prefix-free codes, so they can only be better than that code. So we construct a code E prime that has exactly these log of 1 over qi has exactly these code word lengths. And we construct this as follows. We do this inductively. If the alphabet has only 2 symbols, then there's not much you can do. You just assign each symbol 1 bit. But in that case, if you look at this, log of 1 over pi why is that at most 1/2? That's a good question. That's at least 1 for one of them. Well, the code we use is a single bit. So clearly the cost of the code is just 1. That part's clear. For one of the symbols, pi must be at least 1/2. And so, all right, no, yeah, this is, pi is at most 1. So 1 over pi is at least 1. So log of this is at least 0. And unless one symbol is exactly never happening, which makes no sense. So we assume that that pi is strictly less than 1. So these are at least 0. So if you round it up, it's at least 1. And so if you take 2 to the minus this thing, that gets at most 1/2. Potentially it's smaller. And so then log of 1 over qi is at least 1 if you plug in that inequality. Good, fits together. So the base case is quite easy. In terms of the code, there's not much you can do anyways. If you have at least 3 characters, then we assume that they're sorted by weight. So A1 and A2 are the least frequent one. That's a trick you know from Huffman before. So we merge those two into one character, but now we assign it a new weight, which is just twice the weight of the second weight. So we make the weight a little bigger than what Huffman would have used. And then recurs as in Huffman's code. If those two are exactly the same, if the frequencies of the least frequent symbols are identical, then this does the same as Huffman. But if one of them is slightly smaller, then we know at least this is still summing to 1, to at most 1, because it's from Kraft's inequality again. So that means we can, instead of Q1, also use Q2, and we still get Kraft's inequality. So there was some slack in the rounding. Then we use the code that we construct from the recursive call. There we use the inductive hypothesis to show that this is true, this inequality. So the code word length of this E prime for this character is at most 1 over its weight, and the weight was set to 2q2. And that you can write as log of 1 over q2 minus 1 if you pull it out. And now if you remember what Huffman did, if you lump these two characters together and then recurse, at the end you have to split them again and add this last bit to distinguish the two characters. So that's what we do here. The code word in our constructed code E prime for these two symbols A1 and A2 is the code from before plus this one distinguishing bit. And so the code word for both satisfies this inequality again that we need. And that establishes the inductive step. So if you take that induction together, that shows you how to construct this code E prime that achieves that each code word is bounded by this log of 1 over qi. And then we use what I said before. So the code word length, the expected code word length of E prime is this. And that's at most the entropy plus 1 as we've shown above. And this is some prefix-free code. And Huffman is the cheapest prefix-free code. So it's at most as expensive as that one. All right, I think that was a long proof. Maybe a bit more than a sketch. But I thought it's insightful to show these two things. And in particular, the lower bound, I think, is quite nice and clean. It shows that no matter what you do with the prefix-free code, the entropy is essentially the bound that you get. You can't improve beyond that. I have a little question for you to wake up and join in. It's a quite tricky one, so I'll probably want to discuss the outcomes a bit as well. 20 people. We get a few more. The miraculous appearance of people who are neither in the room nor on the live stream. All right. Let me show the results. So there was quite a few votes for all of them. Almost. Several are right, but this one not necessarily. And I think the important part is what does yield more efficient compression? What I mean by that is kind of what's the best we can show. So if you compare Huffman coding with any fixed character encoding, which means like something like UTF-8 or ASCII, where you fix up front what are the code words that you will use for each character, and the lengths of the code words have to be the same for all the characters. Because both are prefix-free codes, remember, if you have a set of strings that are all the same length, they are prefix-free without any further paying attention. So even a fixed character length encoding, like we've discussed them before, is a prefix-free code, and so Huffman is never worse. So it's always better in the sense of less or equal. It's never worse. Maybe that would have been more precise. These two, when in terms of the bound that we can show, well, what we showed about Huffman codes is that the length of the Huffman code is at most the entropy plus 1. And if that's something I didn't show on the slide, but if you sum this up and all the pi are the same, then this sums up the same term all the time. Then all the pi have to be 1 over sigma. Oh, it's not a nice sigma. So you have 1 over sigma summed up sigma times, that cancels out, and what remains is log of 1 over sigma. Log of 1 over sigma. So that's the entropy if all the probabilities are the same. It's just log of the number of outcomes. So if we plug that in here, that's what we can always show. The length of this code, of this Huffman code, is at most log sigma plus 1. And so these bounds, because of that plus 1, it's not quite clear what happens. Now, because of fixed length character encoding is a code, you will never do worse. Strictly more efficient needs this condition though. So as long as you don't have this condition, you might be just as well. You might do as well with the fixed length code as with the Huffman code. If you have this condition, then there's an additional -1. If the entropy is less than log sigma -1, then this plus 1 cancels, and then so the best you can hope for with the fixed length encoding would be log sigma per character, but you need strictly less with the Huffman code. It's a little edge case in that question. Let's come back to Huffman coding for a second, because that's something I only verbally said last time. So if we encode with Huffman, there's several stages. Usually the first stage is you go through the text and you count how often do all the characters occur. And then you compute the Huffman code for these character frequencies. And then in the second stage, you go through the text a second time, and for each character, you replace it with its code word. The running time for doing that is sigma log sigma to construct the code. If you use a priority queue to maintain the symbol weights, so you maintain a partially built code trie, and the symbols can be these lumped together symbols, right? Remember these boxes that I drew around characters. And they each have a weight. And in each step, we take out the 2 with minimal weight. That's why it's 2 delete mins. And then we do 1 insert, because we combine them and insert the sum again. That's where the, so you get sigma times that operation. And if you do a binary heap, as you've seen in Unit 2, you can implement those in log sigma time. If the characters come already sorted by weight, then you can actually do it in linear time with a neat algorithm using 2 queues. But if the characters do not come sorted, then you somehow have to sort the weights. There's to some degree you don't get around them. That's the time for finding the Huffman code. And the second part is easier. You just need to go through the text one more time. So you need to visit each character in the text, and you replace it with its code. For that, you can just use a table where you use the character as index. And then you get it in this time. So time to read the input plus time to write the output. That's the best one could hope for there. In practice, there's different variations of Huffman codes in use. Some comes from the type-breaking rules. Some comes from the fact that you don't want to do 2 passes. Another thing comes from the fact that, well, Huffman codes are the optimal prefix-free code. They're not unique. You can do different ways. And so you can squeeze out a few more bits if you decide up front how you assign code words. But this is all around the question, how do you encode the Huffman code? And I promise we skip the details on that. So overall, what do we like and don't like about Huffman coding? It's an optimal prefix-free character code, and we always like optimal things because that sounds great. But you always have to listen carefully and check what exactly optimal with respect to what. So in this case, it's the optimal prefix-free character encoding. And it's very fast for decoding. You can use this code trie and just traverse then your linear in the number of bits in the coded text. The 2 passes can be a bit annoying if you want something, if you want to do this. Suppose you're using this in a network router and you want to encode things as they come through. You can't wait, oh, hold back, just please scroll back in time and let me read that again. You might need to buffer everything, and that can be too costly. And also we have to store the code alongside with the text, which means if you're just encoding a short text, might actually be a bad idea to use Huffman codes. I think we can make a little break before we start with this second part. Let's do that now.
smaller than 1, because I think this qi is less than.
Or where does this come from?
This one?
Yeah.
It's less than.
Okay, so you're trying to show the next part. Okay. Yeah, so if q is at most 1/2, 1 over q is at least 2, and then log is at least 1. Yeah, okay, you're right. Yeah, that was about pi, not the qi. Yeah. Question?
Bamboo problem.
Yeah, bamboo problem.
How we can approach it? I mean, one of them is I couldn't solve it actually.
Well, you can always find some solution, I guess. You can always find some schedule. Just
in schedule, for example, second question. There are some numbers. All of them is 4, 4, 4, 4. All of them add. Should we use all of them in schedule, or just, for example, should we use just one time?
Well, you have to visit all the bamboo plants once in a while, otherwise your bound is infinite. So what you probably mean something different. I'm not sure what the question is.
Question is, I mean, the sequence is. For example, sequence is 4, 4, 4, 4, 8, 8, 8, 8.
Okay.
12, 12, 12. I mean, if we do like that, if our sequence it is like that, I mean, I'm saying that should we use all the 4s or all the 8s, all the 12s?
Well, if this is the input, it means there are 12 plants, and they have growth rates 4, 8, or 12. Now, the schedule means which plant do you cut on each day. You definitely have to visit each plant at least once in the schedule, otherwise it will grow indefinitely.
Okay.
But the question is, how can you maybe balance out that these grow much faster than these? So you want to visit those more often. That's clear intuitively, but the question is how exactly, how much more often?
Yeah, but I mean, yeah, you're right.
Yeah, that's it's a puzzle. Yeah. Maybe let's do it after class. We have more questions to discuss. Okay, time to continue. Hope everyone's back and recharged. So in the second part of the compression unit, I'd like to look at repetitive texts in a different sense. The first part was about characters of different frequencies, and then we saw how Huffman can exploit that. Now we'll try to look at repetitions on a bigger scale. I want to motivate this a bit with this maybe well-known example. I don't know. I don't know if this qualifies as a natural text, but more sensible natural text also has the feature that there appear the same words many, many times. Words like the and well, you know, the frequent words in English and in other languages, they just occur many times. But that doesn't necessarily mean that the character frequencies reflect that in exactly the same way. And in this extreme example, I think this becomes quite clear. Suppose this text keeps going over pages and pages, And it's always the same sentence repeated again and again. So if you compute the entropy, which we've seen is a good predictor of how well Huffman will compress this, you will see that the entropy of this text is not so low. In particular, you will have some contribution for each character, and that contribution is the same for every character, no matter how long the text is. That's how entropy works, after all. It goes character by character. And it doesn't in any way recognize that after a certain length, the whole thing just keeps repeating. So if we want to capture that kind of redundancy, anything that's based on Huffman or individual characters just won't work. You have to put in context, several characters at once to get this compressed reasonably. So it seems like the whole notion of compressing one character and replacing it with some code word is not strong enough. Instead, we have to use what's called phrases. So that's just substrings of the text, and replace a whole phrase by some code word. In this case, we would want a phrase that is just this sentence, and then there's some way of saying, just use this code word all the time, and hopefully the code word is much smaller than the sentence. Or maybe there's even a smart way of saying, let's use this code word now so many hundred times. Okay? And we'll see some examples of both of these ways of compressing. Now the challenge, of course, is most texts don't look exactly like that. They have some sort of repetition, but it's not as obvious as this and not as extreme as in this one. The first example of a code that can achieve something like this is a very simple one that's called run length encoding. And that's the simplest form of repetition one could think of. It's runs of the same character. So it's just the same character repeated several times in a row. And it might make sense to have to expect something like this if you think about black-white images that come from a scanner. Maybe it's scanning some page with a high resolution. You want to see all the characters nice in detail. But if you restrict it to 2 colors, we will see many runs of zeros and ones like in this example. For this section, we'll restrict the source alphabet to binary, which is not necessary to do in run length encoding. It just makes the algorithms a little cleaner. I'll comment on this at the end again of this section. It's not a very substantial restriction. The method can generalize. The idea of run length encoding is to use as phrases the runs of this character. So in this case, we have 5 zeros, 3 ones, and 4 zeros. That's slightly more succinct than saying 0, 0, 0, 0, 0, 1, 1, 1, 0, 0, 0, 0, right? Now, if we want to store this, you can, of course, not simply list the numbers. You have to somehow convert that to binary again. And so we need a smart way to do that. But what run length encoding consists of is a little bit more structured. We have to tell the decoder what is the first bit. Do we start with a 0 or with a 1 in the entire string? And then we have to tell it how long each run is. We don't have to store anything else because you always know if I start with 0 and then there's a run of 17 zeros, the next run will be 1s. Otherwise, it would be the same run. So in our example, we store a 0 we start with a 0 and then 5, 3, 4 for the length of those runs. Okay? Easy so far? The question that comes up is, we have these numbers that we want to store. These are some integers. And well, at least in principle, these can grow without any bound. It could be that we get an input where there's a run of zeros of arbitrary length. Could be the entire file. So we have to be prepared to store an integer that we don't know how big it is. It could be as big as, well, we don't know. We don't know up front. So we have to be prepared to store an integer of arbitrary size. How do we do that? How do we do that in binary? And as a start, think about how programming languages do this. That's where the question gets at. Programming languages have to solve a similar problem all the time. They store strings, and the strings have variable length. But computer memory is just long sequence of bytes. There's no specific boundaries. How does a programming language handle this problem? How can it store strings of variable length? Try to be concise. So think about low level. If all your computer has is this, think about a word RAM. Okay, you have one big array and each cell can contain a number. How can you store a string so that a user program can know this is hello world and then it stops without knowing how long the string is in advance? It could be as long as the user gives you an input. Okay, I'll show you some of the suggestions. Okay, this is, you just see the most frequent one. Yeah, I know you will start this game again, of course. No, it always jumps back. I can't scroll fast enough. I think the two main solutions that I know of have been in the list. Shockingly, they're not emoji. Okay, I'll keep you let you keep playing. But so the two solutions I know of. Option one, you prefix the string with the length of the string. So the first entry says now comes a string with 500 characters. So you know the next 500 cells contain characters that belong to this string. Now, there's a slight caveat here. You need to somehow restrict the strings to a length that fits in one word now, right? You have to fit that number in one word. So it's kind of cheating, but it works fine in practice because we don't need strings that are absurdly long. If a word on a computer now is 64-bit, 2 to the 64 is a really big number. Your computers don't usually have 2 to the 64 bytes of memory, not even close to that. And so it's fine. It's a little unsatisfactory in theory, maybe. The other solution is you reserve from the alphabet a special character and say this is the end of the string. And well, C traditionally uses null terminal, so the character that just consists of all zeros. The null character is the marker for the end of the string. It's part of the ASCII alphabet, but it's not allowed to be used inside the string if you use that convention, which is a restriction. And so you need to make sure that the programs obey that, or you enforce it by adding another bit or something like this. Okay, these are the two options. Now what can we do for our integers of arbitrary size? It seems both are, at least from a theoretical perspective, not completely satisfactory. And also we want to do it in binary. Okay. There's a really nice way that is called Elias coding. What we need, just rephrase that a bit in different terminology. We want a prefix-free encoding for integers. Why prefix-free? Because we want to decode it, and that has helped us in the past, so let's stick with that property. But we want it to allow arbitrarily large integers. There should be no baked-in bound like in this store the length of the string first version. And we need to know when we're done. That comes with the prefix freeness, but this essentially means we cannot simply write down the binary representation of the number, because then we wouldn't know when one number stops and the next begins. What you probably didn't think about, but is completely obvious in hindsight maybe, is there is a simple encoding that satisfies both of these properties fine. That's the unary encoding. That's if you make ticks on the board to count something. I can represent a number by that many zeros followed by a 1 to signal the end. If I have two symbols and I only use one to represent the numbers, I have another one free for the end of word symbol. It's just that we don't like this encoding because it gets really long for even moderate numbers. So that's not great, but it exists, right? It's fine. Now it's much too long, and in a sense, the output has long runs, and we want to use this for compressing runs, so that seems to get us nowhere. Now the trick in Elias codes is the unary encoding of the number itself is crappy long, but what if we take the binary representation of a number, which didn't work by itself because we don't know how long it is. But we know to store a number in unary. So we store the length of the binary representation in unary using exactly that idea, and then append the actual representation. That doubles the number of bits that we need compared to just the binary representation, but it makes it prefix free. And that's called Elias gamma code. Okay, I lied a little bit. Elias gamma code is a very slight refinement of that idea, because immediately if you do that, you notice two things. The length of the binary representation is always at least 1. We only represent natural numbers starting with 1. So we might as well store the length minus 1 instead of the length. Saves a bit. And the second observation is the binary representation of the number always starts with a 1 because we don't want leading zeros. And so we don't need the terminating 1 of this run length encoding either, just because there is always a 1 coming with what we append next. So, but with these two slide modifications, this idea is what's behind Elias gamma codes. So here are some examples. 1 is just mapped to 1. Now, how's that? 1 in binary is a single 1. The length of that is 1. We store not the length, but length minus 1. So we store 0 zeros followed by the binary representation, which is just 1. 0 zeros, 1 1. Okay? How does 3 work? 3 in binary is 1 1. The length of that is 2. Take off 1 means I have to put 1 0 in front of it. So 0, 1 1. Let's do 5 as well. 101 is 5 in binary. And so I prepend 2 zeros, 1 less than I have digits. And for 30, well, you can hopefully figure out that 1 1 1 1 0 is 30 in binary. Yeah, 31 is 5 1, so that looks good. And so we prepend 4 zeros because we have 5 digits in the binary representation. Okay? Apart from the brutal task of computing the binary representation of numbers, this is not too hard to do. Let's see if you got this one. Let's do the opposite. We decode. And to make it not so boring, I added more bits. So what you see here is a string that contains a number and other garbage after it. And you're just supposed to decode the first number that's encoded with this Elias code. Okay? I think you have the string in the question, so let me maybe go back to the slide with the instructions. And please send me the number in decimal, not in, you know, whatever that is. They're emoji for digits, right? How did you make one answer appear in colored? Is this also in that view? Okay, I haven't shown the... okay, a few more minutes. Okay, I'm not sure what the color code means. I'll show some answers because I want to get through some more exciting stuff too. I think the colors are just how often it was answered. Various things. Let's just go through this so that we do it once together. How do you start? First, you check how many zeros do we have. 3 zeros. That means the number I'm reading has 4 digits. So I have to take these 4. Sorry. That's the number I have to decode. So what is... Okay, you don't see it. All right, sorry for that. The first 3 zeros tell you need to read 4 bits. These are the 4 bits. Now, what's that number in decimal? 4 ones would be 15. So take off 2 would be 13. That's among the options, at least. You will get some more practice for this one. And here are some examples how this is used in run length encoding. Remember, what we do in run length encoding is we store the first bit, starts with 0 or starts with 1. And then what follows is a sequence of these run lengths encoded using our new favorite toy, the Elias code. Very excited seagulls. Okay, let's go through some examples. We store a 1 because the first run here is with 1s, not 0s. How many 1s are this? 7-ish. So we need to store the number 7. Let's do this one more time. 7 is 111 in binary. So I prepend 2 zeros to signal that the length is 3. Okay? Now we have 2 zeros. That's in binary 1 0. Prepend the 0 for length 2. A 1 is mapped to a 1. We've seen that example before. These are 20 zeros. I believe my slides 20, I hope, is this in binary 5 digits. So I prepend 4 zeros. Okay? Got the idea? One more for 11. 11 is this in binary, prepend 3 zeros, and there you go. Let's try to see, well, in this example, it worked quite well, compressed it down to 63%. Let's do one more example of decoding. So first step, the first 0, is this pen? The first 0 says, we start with a run of zeros. Then come 3 more zeros. So the length of the number we're reading is 4. So we take these 4. That was 13. So we produce 13 zeros in the output. Then we keep going. The next 2 numbers, we have 2 zeros. So we need the next 3 bits. That's 1 0 0, otherwise known as 4. So we append 4 ones. We read 0 zeros before the next one. So we read just 1 bit, and that is a 1. So we append 1, whatever the next thing is, zeros. There you go. And one last one, we read 1 0. That means we read 2 more bits, 1 0, which is known as 2. So append 2 ones. That's how run length encoding and decoding works. Okay. Now, if you don't have a binary alphabet, this alternation between zeros and ones no longer is enough. Instead, you have to say which is the next character. There's probably no way around this. and then you need to maybe come up with a smart way how do you best encode that. Other than that, run length encoding also works for bigger alphabets. You can just write down a pair, now comes character A, so many times, and the so many times is again Elias gamma coded. And this is used in isolation. To be honest, run length encoding isn't that great, but it's used in some old formats at least. It is a quite simple algorithm, and so can also be implemented very quickly, to run very quickly. And it's a part, other than the Huffman code, which could essentially always just cut a text down to some smaller constants times n for a fixed alphabet. The run length encoding can be extremely effective if the input is extremely boring. And the ultimate case is if you have a file that's just n zeros, then run length encoding would find a single run and encode that using 2 log n bits. Right, log n for writing down n in binary and prepend as many zeros, -1. So that's a reduction from n to log n as a really strong compression. But of course, it only works in these very extreme cases if you have very few runs. More realistically, for most types of data in isolation, the compression is negligible. And so if you compare exactly how many bits you use, up to runs of length 6, you don't save anything. And for the specific numbers 2 and 6, the gamma code is longer than a run of that length. So you have expansion for some inputs, and you have compression for ones that have very long runs, more than 6. Remember, this was this no free lunch theorem that you will look at tomorrow in the tutorials, today or tomorrow. No? Maybe. So compression can't always work. You will always have, for each compression method, some inputs where it only makes things worse. Yep. Not at all. So the question was, how do you code a single zero? And okay, tons of the trick here is that we don't allow 0 in the alphabet, so it's just forbidden. If you wanted to allow a 0, then you would have to maybe just encode n+1 instead of this, or you can twist it a bit if you need a 0. For run lengths, we don't need a 0, so that's why it's forbidden. Okay, we can definitely do the encoding. Let me jump right into this. In this section, we'll see the first compression method that already, as it is shown here, is competitive in applications. That's the Lempel-Ziff-Welch method, but you would probably better know it as variance of zip. And Lempel-Ziff is an entire family of compression algorithms. And this is one specific example that is arguably the cleanest to show. They all have similar flavors, and so it doesn't matter too much. But I definitely want to stress that whenever you use programs like zip, gzip, and their variations, they build on ideas around that and add more bells and whistles to it. But the core idea is what's coming up in this lecture. To motivate this, let's do a little toy example. Without much saying, without any further instructions, head over to Slido and tell me what the second to last line of that poem is. I'll leave the slide up, but this idea of presenting things in this activity is taken from Computer Science Unplugged, which is a lovely resource for explaining computer science concepts in a really approachable way and without computers, hence the name. There's many other cool things there, but This is from their compression unit. In case you're like me and you wondered what peas porridge would be, that's shown in the picture. I was told some Northern English dish, but I haven't yet found a local to confirm this. It's not Northwest. It's, yeah. And I'm not sure about 9 days old. Okay, votes are coming in. I don't know, let's briefly show them for the record. So what you've probably figured out without me telling you much, there's arrows that mean for certain boxes you have to go somewhere else and look up what the box stands for. And for, at least for these kind of extreme cases, like this very repetitive poem, you only get to write a small number of letters explicitly, and all the others can be referred to. The visual impression that you just store maybe a third of the characters is a little misleading, because the arrows also need to be represented somehow if you encode it. But the key idea is that's what's behind Lempel-Ziff. Try to reuse things you've seen before. Okay? Yeah, of course, the poem reads, peas porridge hot, peas porridge cold, peas porridge in the pot, 9 days old. Some like it hot, some like it cold, some like it in the pot, 9 days old. Let's try to put that into slightly more structured language. What we said before is, what we looked at before is always looking at single characters. And already this motivating example from The Shining is showing that this is not exactly capturing all the sorts of repetitions that we find. And here's some examples where we have this repetition. I mentioned frequent words in English. But there's also other applications. If you have HTML websites, there's lots of tags that appear all over the place again. And these will be repetitions. And there you find bigger structures that are repeated many times as well. So to capture this, we need a different idea. Lempel-Ziff is a whole family of such compression algorithms. And as in the poem, you store things by referring to things you've seen before. What you can store more specifically in Lempel-Ziff or Lempel-Ziff-Welsh is either a single character or a substring of the text of the part that you've already encoded. There are many variants of roughly the same idea, which essentially differ in how you find the thing you want to refer to and how you store the thing, how you store these pointers back to a different box. I just listed these because I think they cover many key phrases you might recognize, but this is not something you need to know. Which one exactly is in which program? The variant I want to discuss is Lempel-Ziff-Welsh. So there's a third person who invented a part of it, whereas Lempel-Ziff were the founding fathers of the idea, if you want. All of these Lempel-Ziff codes are variable to fixed encodings, which is supposed to mean a variable length portion of the text is encoded using a fixed size code word. So you will have a fixed size, a fixed list of things you can refer to, but the things they can refer to can be of arbitrary size in principle. A practical choice is having 12 bits or something around that for these code words, but that's not written in stone. What these methods do is they maintain a dictionary of strings or phrases that you can use in encoding the next portion of the text. That's why they are also sometimes called dictionary encoding. I'll denote this by D. Because the code words have k bits, you have 2 to the k entries in this dictionary. And each entry in the dictionary, they're just numbered, and that's the code word. Okay? So it's the indices in that dictionary. We always fill initially the first positions in the dictionary with the single symbols from the alphabet. We need that to get started. And then whenever we encode one portion of the text, we add something new to the dictionary. And maybe let me explain that in the picture. So we store something new. In this case, ban is a string I found in my dictionary before, so I use that. And I add to my dictionary the new string where I take one more character. So whenever I use a phrase, I insert into my dictionary a new phrase that's one character longer. And well, this is not clear here yet, but we'll make sure that whenever I take a phrase, this is also the longest phrase I could have taken. The trick here is to make this so that the decoder can also replicate the same process. And so you have to be a bit careful in doing that. But we'll see how that goes. Let's do an example, explain the algorithm on an example. And that might make it a little clearer how this works. So here we use the ASCII alphabet. So there's a quite long table for all the letters, etc., as you've seen on last time. And so I only show the ones that actually occur in the text. But the indices are as they would be for full ASCII. And then there's more entries in the dictionary that are currently empty. And they will be filled once in a while we're going. Initially, so what we do is always try to find the longest next portion of the text that occurs as a phrase in our dictionary. Sometimes we find several strings. In fact, we will most of the time find a shorter string that's already in the dictionary, and then a longer is also in the dictionary. We always take the longest match. So we try to find the longest string starting from the current position that we find in the dictionary. But initially, we have only the single letters, so we just take y. Its code is 89. And so that's the first code that we output. But we're not done yet. Remember, whenever we produce something, we insert a new phrase into the dictionary, and that is the phrase we stored plus one more character. So we insert yo into the dictionary as a new string to use in the future. Okay? Next step is a single O, because we haven't seen anything that starts with an O yet. So we just encode the single character again. O is here. But we do add another string to the dictionary, O plus one more character. All right? Next one, we haven't seen exclamation mark, so nothing happens, just a single character, same game. We insert one more phrase into the string, into the dictionary. Space is new. Again, we can't find a longer string, but we insert one for later. And now for the first time, something interesting happens. We have y in the dictionary, but also yo. And so we use this as the longest match we can find, and use this new code to represent that two-character string. And we also add a new string to the dictionary, which is one character longer, taking the one new character from the text. Okay? U we haven't seen, so nothing interesting happens. The exclamation mark we've seen before, and it was followed by a space before. So we can reuse this two-character string. And we insert another three-character string where we have this combination. Okay? And now I guess you start getting the hang of it. The longest next thing is U. We find it here. So we use that code, and we make the one bigger string part of the dictionary. There he goes, your. R we haven't seen, so nothing interesting happens. Then space, but we have seen space y before, so we can use that again. One more. Okay, O we have seen, but OY we have not seen yet. So we can only use the O, but then insert OY. Then we see another yo. We haven't seen yo with an exclamation mark behind. That's it. And one more, and then we're done. If you're worried about how to find this longest string that is in the dictionary, a convenient way to store the dictionary for the encoding step is to store it as a trie. Now we'll have to modify our notion of trie because we essentially have not prefix-free sets of strings here. Indeed, all the longer strings by definition have a prefix that's already in the dictionary. And so we have to use an extended version of the trie where we allow values in the internal nodes. But other than that, that's a convenient way to find the longest match, because you start traversing the trie in the root with the next character and you follow down as long as you can. And the first character that doesn't match is the one that you have to add to the dictionary after that. The node where you stop tells you what character to use. So instead of this table, which is convenient to show to you, you want to use a trie to make this efficient. Here's that idea spelled out in code. The dictionary is stored as a trie here. We keep the next free code word, so the next row, the next index of the row in the dictionary. And we keep X as the previous phrase that we used, because remember, we have to insert that into the dictionary. Okay, so then we iterate through the text. That's this outer loop. We take the next character of the text. And then we ask the dictionary, have you seen whatever was the previous step plus this new character? And if so, then we go one step down in the trie. And we continue with the for loop. So we try to find the longest match. As long as we can traverse an edge in the trie, we keep doing that. When for the first time X was in the trie, but XC no longer is, we jump into this else branch. Then we get the code for X without C, which was a mismatch, and append that to the coded text. And we put XC into the dictionary because that's our new code word. And that's all for the encoding. And I guess we'll have to wait till Monday to see how we can possibly decode that again. All right, see you next week. Any bamboo questions? I'm still here.